Of all the chemicals involved, we put in MgO subscript S. The next step is to put in the enthalpy of formation of the ionic salt. Now, to make 1 mole of MgO, we clearly need 1 mole of magnesium atoms and 1 mole of oxygen atoms. And we have to form that from the elements as they exist under standard conditions. The magnesium exists as a metal, and therefore we need just 1 mole of Mg. Shouldn't bother putting the 1 in there. And we need 1 mole of oxygen atoms. Now, oxygen exists as a diatomic gas, so in fact then we need a half a mole of O2. And the state symbols are very important here. At room temperature pressure, magnesium exists as a solid and oxygen exists as a gas. This particular value has been given. This is the enthalpy of formation, and the value provided is minus 602. Now, the next thing that we do is we'll take a look at the magnesium. And the first thing that I have to do with the magnesium is change it from solid magnesium into gaseous magnesium. There are 2 names for this. It can be referred to as the enthalpy of atomization, but it can also be referred to as the enthalpy of sublimation. We are, after all, changing 1 mole of magnesium solid into 1 mole of magnesium gas. So we go from Mg subscript S to Mg subscript G. Nothing has happened. The oxygen remains as it was. The energy change for this, the enthalpy of atomization of magnesium, has been provided and is plus 150. Next we look at the ionization of the magnesium atoms, the gaseous magnesium atoms. Now, magnesium does lose 2 electrons, but we have to do this as 2 separate steps. In the first step, we will remove 1 electron, and therefore we will get Mg plus gaseous. The oxygen remains unchanged at this stage, but we must bear in mind that the magnesium has lost an electron, and to balance this equation we must have E minus as well. This is known as the first ionization energy of magnesium, and the value given in this question is plus 736. And then we move on to the second ionization energy of magnesium, converting Mg plus gaseous into Mg2 plus gaseous. Nothing has happened to the oxygen. We've generated another electron, so we have 2 E minus. And the second ionization energy of magnesium is going to be much larger than the first. Once you've removed the first electron, the nucleus will be able to pull stronger on the remaining electrons. And so it's not surprising to find that the second ionization energy is around about twice as big at plus 1450, provided in the question. Now we turn to look at the oxygen. The first thing we've got to do is to split the oxygen from diatomic molecules up into its separate atoms. So nothing's happened to magnesium, still 2 plus gaseous. But this time we change the oxygen, the half O2, we split them up into oxygen atoms. I've done nothing to the electrons, so they're still there. And the oxygen now is in the form of gaseous atoms. Here again there are 2 names for this process. What I have done is to split half a mole of oxygen molecules into a mole of oxygen atoms. So what I'm looking for is the enthalpy of atomization of oxygen. But alternatively, one could be provided with the bond energy of oxygen. However, when one refers to the bond energy of oxygen, we're looking at the energy associated with breaking 1 mole of these oxygen bonds, these O double bond O's. In this case, we're only breaking a half a mole of oxygen bonds, and therefore we require only half the bond enthalpy. The bond enthalpy has been provided in this question as 496, and I will therefore divide that value by 2, giving me a figure of plus 248 for that particular energy change. So now we've got gaseous 2 plus ions of magnesium, and we've got gaseous oxygen atoms as well as these 2 electrons. The next step is the first electron affinity of oxygen. Now when the electron goes into the oxygen atom, a new attraction is formed between that electron and the positive nucleus. And when a new attraction is formed, like a new bond being formed, that's an exothermic process and energy is released. So in this particular case we're going to, nothing's happened to magnesium, still 2 plus gaseous, but the oxygen now has gained one of these 2 electrons and has formed O minus gaseous. And since one of the electrons has been used, we now only have plus E minus. And this is known as the first electron affinity of oxygen, and in this question it has been given as minus 142. The next thing to happen, the next event, is the second electron affinity of oxygen, and it hasn't been provided. The question is, why did I choose to go up the way? Well, going up the way simply represents the fact that this step is an endothermic process. There's an increase in enthalpy. When it comes to adding the second electron, there are 2 separate things that happen. Yes, you do get an attraction between that negative electron and the positive nucleus, but also you have a counter effect because that electron pairs up with an electron that's already in there, causing repulsions. And it simply must be the case that the repulsions win out over the new attraction that is formed. So we're expecting here a positive value in the second ionization energy. The last of the steps is this step. Then we need at least to present what happens in terms of an equation. Nothing happens to the magnesium. They remain as 2 plus ions. But the oxygen is going to gain this electron. The O minus is going to gain that electron to form O2 minus, gaseous, and the electrons have now both been used up, so electrons no longer appear in the equation. What we have are gaseous magnesium ions, gaseous oxide ions, forming magnesium oxide, which is the lattice enthalpy of formation. And the lattice enthalpy of formation is a very exothermic value, minus 3889. So we have the enthalpy change for 7 of these 8 steps. What I now need to do is find the energy change to go from here to there, the second electron affinity of oxygen. I can't go this way, but what I can do is take an alternative route, and the energy change should be the same. So I'm going to go up this way, then down here, down here, down here, down here, down here, cross and up, and that will bring me to that position. I've got to keep an eye on the direction of the arrows, and if the arrow isn't pointing in the direction that I'm going, I have to change the sign on the energy value. So if you've got your calculator, put the following values in as we call them out. We're starting here, remember, so we're going up. The energy change says minus 142, but it's going in the wrong direction. So into your calculator you put the value plus 142. Now we're going to go down through a series of steps. The arrows are pointing in the wrong direction, so in each case I will change the sign. Currently you have 142 on your calculator. This step requires you now to put the value minus 248. So you started with the value plus 142. You now go minus 248. This then has minus 1450. That's minus 1450. This value is minus 736. This value is minus 150. This value is minus 602. And this value here is going to be positive because we're heading up the way. So we have to put in plus 3,889. And if you've done all that correctly, you should have come out with a value of plus 845 kilojoules per mole.